Hi everyone, and welcome to a new episode in the Multiverse video series. Today we're going to learn how to diagnose and optimize GPU issues with TensorFlow and R. Now, this is a bit of a follow-up video from one of our previous videos where we actually trained, well, we didn't train, but we built an AlexNet model with TensorFlow and R. So basically what we did in the past video was we took a look at the paper and we translated the paper to our best knowledge to code that was using Keras, TensorFlow, and R. Now, one of the things that I mentioned at the end of that video is that, like we were training on my local machine, and I mentioned that running on a GPU should be much faster. And, like usually that should be the case, like just moving stuff to the GPU. If you get a machine with a GPU, things should get faster. But as we'll see in this video, that is not necessarily the case all of the time. And you might need to kind of like troubleshoot a little bit, kind of like what's going on, and consider a few options when, when running your models in a GPU. So for this particular video, what we're using Google Cloud Compute. We already presented in a previous video how to set up Google Cloud instance with GPU support for TensorFlow and like R and RStudio. And the way that we did that in the past was using the MLverse Docker image, which for this video it has been updated, and now it's kind of like simplified and only installs RStudio server. And yeah, so it should be much easier to get up and running. But you can take a look at the repo, and I'll post all the links in the YouTube video on the description. And yeah, so just as a quick kind of recap and new changes that have happened in in the next recent months since we recorded the last video. Well, it's still pretty easy to get Google Cloud instance. So all you need to do is say create instance. And basically you want to select still from the available images. You want to choose the deep learning on Linux category. Now, kind of like a good reminder is that even though there's a lot of like images that you can choose from, really the only one that works is the first one, which is the GPU optimized image. All the other images are optimized for TensorFlow processing units, so they don't actually come with CUDA installed. And you need to have CUDA installed to use TensorFlow and GPUs in this particular image. And the other thing to notice is that currently they only support CUDA 10.0. And so if you're trying to use TensorFlow 2.1 or 2.2, beware that it would require CUDA 10.1. So what I recommend for this video, if you're using Google Cloud Compute or similar services, it's use the image that they provide, which in this case it's TensorFlow 2.0 with CUDA 10, and just don't install anything from R. Just use the base installation that they provide. And that should save you some time rather than having to reinstall CUDA and like then the right version of TensorFlow or whatever. Anyway, so all I did was that, and then I selected the GPU version, which you can do here by saying add GPU. And in my particular case for this video, I use a Tesla K80, but you can use like a Tesla V100 or whatever. All right, so that kind of like covers the setup that I have for this video. Is just a remote instance running on Google Cloud Compute and RStudio server, which by default runs after you run the Docker image. So this is what we're left with. We basically have RStudio server running in this particular cloud instance, and the code that we use on that we came up with in the past video. But let's take a look at this. So if we were to execute this particular code, which we want to do, so let's just clear this session. We're gonna restart everything. And we're basically gonna run the code that we came up with on our previous video. So yeah, so the session is restarted and we have TensorFlow here, which is great. So, like one of the things that you can do, first you want to verify that, for instance, you have CUDA installed, right? Which, depending on your system, it might be a little bit different. But in our case, we can just go to CUDA and then versions. And so here we know that we have CUDA installed. We also know that we have a GPU installed from the instances that we chose. So in theory, all we have to do is, well, first of all, install a couple dependencies, which in this case I did as follows. I did Python M, and then pip, and then install, and then SciPy, which was already installed, and pillow. And I'm running it directly on the command because I want to use the infrastructure that TensorFlow, well, this TensorFlow image already provides, rather than using reticulate or try to upgrade anything from R. So I'm just using the functionality that is already on the base image. So you run that, and then we can, like import Keras as usual, download tiny ImageNet and with the pins package, and then just basically get the path to that data set, which I mentioned on the past video that it's already really nicely structured, because each category, each folder contains a category, which is what we need from flow from images. All right, so here again, I believe if we look at the logs, we should see that we're using a device of type GPU, which is correct, which is what we have here. So everything is looking great. We compile our model, then we, yes, the data augmentation step, and then we basically flow the images from the directory. And the first thing that I noticed while I was running this for the first time is like, well, things are not that fast. As you remember, I run it last time on my local computer, and then I run it on this GPU instance, and things were as slow as they were on my computer. So, like a couple of things to kind of like notice while you're troubleshooting these things, right? So the first one is, all right, we know that things are running. What is going on, right? And so the first thing that you can do is just use the handy top command. This has nothing to do with GPUs whatsoever, but in Linux, it will give you like a nice view of what's going on, right? And at least we can see here that we're using, CPU, right, significantly. And, that's fine. We're doing some processing as we are training AlexNet. But what we really want to focus on is we want to take a look at basically what's happening on the GPU, right? And for this, the first command that you can use is a command from Nvidia, which is Nvidia SMI. So this will give you a snapshot of what's going on the GPU, right? And as you can see here, we do have our GPU properly configured, but currently it's using 0% of that particular GPU, right? So that's not good, right? We can actually kind of like validate this with another tool, because like the first reaction could be, well, maybe TensorFlow is not using the GPU. That's not the case. We know that TensorFlow is using the GPU because we saw it on the logs. It got detected as a GPU somewhere in here. So we know that TensorFlow is using a GPU. So the other command that I recommend using, and I had to pre-install this before kind of like getting started with this video. It's called nvtop, and you can go to their GitHub repo. I'll post it on the link on the description file. And yeah, basically, if you're using Ubuntu 19, which I'm not, you can just run this command. Since we're using Ubuntu 18, what I had to do was install a couple dependencies and then run cmake. Wait, where are the instructions? Actually, those are not the instructions. Sorry, the instructions are these ones. So basically, follow the nvtop build. Yes. So basically, you need to clone the repo, run, create a directory, run cmake, runs cmake, and then run make, and then installed. I had to run these with sudo, but that's about it. And then you end up having what I'm going to show you, which is a bit of kind of like, I think, a bit more detailed view of what's going on the GPU. So we can say bin, which is nvtop. All right, so here what we can see is kind of like with a little bit more detail what exactly the GPU is doing. So the good news is that the GPU is being used. So you can see the GPU being used in these spikes, and it's being used up to 75% of the time. But still, like, things are almost as slow as processing with a CPU. And you know, there could be multiple ways of troubleshooting this. I was lucky enough to have been able to talk with Sigrid and Daniel, which work on the TensorFlow R team. And yeah, so kind of like, you know, like the suggestion that I got from Sigrid was to use, rather than using flow images from Director, to use Daniel's unit, kind of like a model, well, example that he came up with on the on the unit model. And basically what the unit model does, and you know, it's in the blog post and it's also on the GitHub repo for the unit model, it uses tfdatasets. And basically it comes down to the problem here is that flow images from directory is not very efficient. So a lot of the time is being wasted actually loading the image, resizing the image. Like, as you can see here in the in our data augmentation step, we're doing things like shifting the range, changing, basically shifting the image and flipping it, and computing CCA widening. And all those operations are probably happening on the CPU, and it's not very efficient. So unless you pre-process all your images, you're gonna get stuck not using your CPU at a, you know, at its 100%, or at least using it at all. Like in this case, like really, as you can see here, the GPU is being used very, very little. So how do we fix that? Well, first of all, let's we'll stop this. And what we want to do instead is we're gonna stop training. So what we're gonna do instead is we're gonna follow the approach from the unit blog post and unit model. And basically what that does is it makes use of tfdatasets, and you know, it creates a table for the images and then for the output, which in this, I mean, for unit is the mask, like the actual region that we're computing for the object. In our case, the output is just the categories, right? Is the categories that we're using to is the categories that we're using to classify the images on the using the AlexNet model that come from TinyImageNet. So so that's kind of like one difference. And then in this case, you know, we also have like some pre-processing steps. So for instance, here what we're doing, let's see, well, we're changing the type to float because that's more efficient, but we're also resizing the images. And we have a helper function here that is adding brightness, contrast, and saturation. So basically what I end up doing is I literally copy pasted this code. And what I end up doing was adapting it for the AlexNet model. So if we take a look at the modified AlexNet model, basically it still loads the images from using pins and ImageNet, TinyImageNet. But then what we do is we basically create categories for those images, and once we have the categories, we basically transfer them to a categorical variable. Yeah, that's pretty much it. So now we have our categorical variable, that's the output, and the input is still images. And then we're using the same transformations from the unit models, which is we're adding brightness, contrast, saturation. We make sure that we're clipping them just to make sure that the values are between 0 and 1. And we also have a helper, we have our helper create dataset function here that basically resizes the image and converts them from 8-bit to float 32 as inputs to our first layer in our AlexNet model. So that's pretty much it. So it's, it was pretty straightforward. One caveat here is that I don't have CCA whitening or the PCA step that was mentioned on the AlexNet model. If I have some time, maybe I'll add it. But if not, I'm still interested in running this on a GPU and seeing the difference between kind of like running it on a CPU and a GPU with proper optimization steps on top of what we already have. Right, so let's try to do that. So for that, I'm gonna restart again. I'm gonna restart the R session and start clean with this script. And then basically what we want to do is we're just gonna run this script, which again, getting the images from ImageNet, tiny ImageNet, which happens to be a subset with 200 categories. And then once we have that, we're basically creating our categorical variables and creating our AlexNet sequential model, loading AlexNet into it. Again, as you can see here, we have the GPU is still active, which is good. And then we're compiling our model. We're using our data augmentation function, defining our dataset creation function, and then we are ready to train. So yeah, so now we're training, and as you can see, it's gonna be significantly faster. So you can take a look at this, and yeah, there's no comparison. I actually took the numbers to compare them, and now that we're using properly tfdatasets, this process is about 10 times faster than using a CPU or a GPU with the slow flow from image function that we were using before. And again, we can take a look at Nvidia SMI, and you can see here that now we're using 61% of the GPU resources, which is definitely an improvement from what we had before. And again, I like this tool nvtop. I think you can get away with not installing it, but it's worth taking a look at it if that's if you feel like perhaps your GPU is not being used as much as you think it should be using. And again, yeah, this is getting trained. It's probably gonna finish the first epoch in about a minute compared to like the 10 minutes or more that was taking when using just not tfdatasets. So now that we're using tfdatasets, which happens to do some of the operations on the GPU, we see that, yeah, I mean, this particular GPU is being used at about 60%. Now, I'm not sure yet. I haven't investigated what we would have to do to go beyond 60%. One of the hunches that I have is that, as you can see here, we're still using a significant amount of CPU. So, like it could be possible that if I were to get a slightly bigger instance, which in this case I'm only using 4 CPUs, it might be worth using 8 or even 16 CPUs just to make sure that we have enough bandwidth to, just to make sure that we actually have enough bandwidth to process all the data from disk into the GPU. And that might actually help us improve the performance of the usage that we have on the GPU a little bit higher than what we have right now, which is about 50–60%. But again, like this is so much better than what we had before. So definitely an improvement. All right, well, that's about it for this video. I wanted to make sure that, even though my hope was to start training ImageNet directly, like this week I had to spend some time actually optimizing the previous model that we have with AlexNet to actually get it to run properly on a GPU. I'm sure there's other improvements that we can do, but I feel like it's already good enough that we're using a good amount of the GPU. For our next video, what we want to do is, I think what I'm gonna do is I'm gonna try to actually run rerun this particular data set, but with multiple GPUs. Again, right now we only have one GPU. So we're going to run with multiple GPUs, and I think we're ready to try to run against ImageNet. Well, actually, before we get into running ImageNet, I expect one of the problems that we're going to hit is that we will have to pre-process ImageNet properly. So currently, we're using this really nice data set from Stanford, which they already pre-process ImageNet, and like it's on a nice, ready-to-use format. So actually, I think what we're going to have to do for the next video is just make sure that we can load ImageNet from the real ImageNet dataset by loading it from Kaggle, or why not? So we'll do that, and if we had enough time, we'll also start training ImageNet with a few GPUs and see how far we can get. If you want to keep track of the new videos that we're creating, make sure that you subscribe. We try to post one video each week, and kind of like we'll keep doing progress with this. Definitely, if this is the first video that you're watching, you can go back in these sessions of kind of like training, performing distributed training with multiple GPUs and across multiple computers. And yeah, we'll keep you posted. And yeah, definitely subscribe if you want to keep in touch with the work that we're doing. So thank you.